Okay, I think we are live. Yep, everything seems to be in order. Sorry about the technical issues last week. Everything has now been sorted. All right, let's get started now. So last week, this is going to be somewhat longer than the past few weeks. So yeah, let's get started. So last week we talked a little bit about sets, maps, and dictionaries. And we learned essentially how we can use a hash table or a dictionary or a set instead of an ordinary array or list to improve the efficiency of an algorithm. We also learned how to implement those data structures in Python and how to use their associated methods to solve some actual programming contest problems. So we learned about sets, maps, and dictionaries. So we learned that, first of all, with sets, we can add in constant time. O1 just means constant time. We can remove in constant time as well. And we can check membership, which means check if an element X is in a set S in constant time. All right. We also learned that we could do this with dictionaries, and we also had this lookup feature. So we had lookup value for a key was also constant time. So what we're going to do this week is use this knowledge to implement a new data structure called a graph or a network. We're also going to discuss methods for visiting the nodes in a graph in an efficient manner. So let's talk a little bit about graphs. So graphs. Okay, I'm not sure if everyone has heard the term graph or network. I think the term network will probably be a bit more familiar. But graphs appear constantly in everyday life. There are lots of things that are networks. For example, the platform which I'm streaming this workshop, the internet, is a network. So the internet is a network. So we have social networks, which are networks of friendships. We have electrical networks. Things like roads, those are networks too. Transportation. All of these things are very, very kind of examples of the same abstract structure, which is called a network or a graph. So what actually is what is a graph or what is a network? So in a very abstract sense, a graph or network is a set of vertices connected by edges. So what do I mean by vertices and edges? Okay, here's an example. We have a bunch of dots like this, and maybe there are some connections between them. Maybe this might be a connection, or this. For example, these might be connections between some of the dots. So we have dots that are connected by lines, and the dots are called vertices, and the lines are called edges. Simple enough. But this concept is all pervades everyday life, and it pervades computer science. All right. So for example, let's look at social networks. Okay. In a social network, the dots or the vertices might be people. So for example, people are the dots or the vertices, and the edges might be the friendships between people. So this edge here, this line, might be a friendship. Okay? We can have other types of networks. For example, a computer network is just a network of computers that are connected by some sort of wireless connection. So the nodes or the vertices, dots, are just computers, and the edges or the lines are basically just like some sort of wireless connection between the computers, or if they share information or something like that. All right. So this concept is very important. Now, there's one thing we should take notice of, and that's the fact that it doesn't really matter which way you draw the structure. The actual information in the structure is what matters. So let me draw something. So for example, let's say I have 3 dots, A, B, and C, and I draw them in a circle, or if I draw them like this, for example, right? This is the same as just this, A, B, C. The actual shape doesn't matter, just the information, which is just what the dots are, what the vertices are, and what edges are connected between the vertices. Fair enough? Okay, let's keep going. So, so the way the graph looks, doesn't matter. We could equally have drawn this as BAC, like this, like a triangle sort of structure. It wouldn't have made any difference. These are all the same graph because they all contain the same vertices and these particular edges. Okay, so how might we describe a graph in a computer? So here's one way. Okay, we might say we might have a dictionary, and we'll do this. We'll say A is connected to B. So A's value is a list which contains B. B is connected to A and C. So we'll make a list which has a key of B and a value of A and C. And C is connected only to B. So comma, C is connected to B. Does that make sense? So we have a dictionary where the keys are the vertices, and the values are a list of vertices that are connected to the key. So what I mean by that is that what is A connected to? It is only connected to B. So the value of A in that dictionary is only going to be a list which contains just B. B is connected to two vertices, A and C, so we should store these edge connections in a list, so B is connected to A and C, a list of A and C. So we hash a node, so we hash a node or vertex to a list of its neighbors. Yeah, that's a better way of saying it. So essentially for each vertex, we're storing who are their neighbors. Alright, that makes sense. So that's how we can implement a graph as a dictionary in Python. So let's now look at an example problem where we basically need to essentially interpret information as a graph and try and figure it out. Alright, here we go. Let's turn off our video feed and let's read this problem. So first of all, we'll read the time limit. It's 1 second, which means our program needs to answer all of the, or produce all of the output that it needs to within 1 second. So we're looking at something that takes linear time-ish. Alright? Okay. Well, depends on the size of the problem, obviously. If we have like n equals 100,000, or in this case f equals 100,000, oh sorry, 1 million. Yeah, we're looking at something that's linear time. Okay, let's read the problem now. The face of electronic gaming has changed dramatically over the past few decades. Forget text adventure games and rickety asteroid cabinets. These days, it's all about ultra-realistic graphics, motion sensing wands, and high-end CPUs. But despite this, simple games with basic rules and crisp art are doing as well as ever. One such game is Friendlist, a multiplayer game requiring nothing more than an internet browser to play. Okay, this is all irrelevant information, but it leads on to the problem. In Friendlist, players add each other as friends based on looks, reputation, or even real-life connections. Friendship is mutual. If Alice has Bob as a friend, then Bob has Alice as a friend too. Of course, okay, so this is something that I didn't state earlier. So we kind of assumed that these sorts of relationships are mutual. So if like A has B as a neighbor, then B also has A as a neighbor. But we could also draw arrows on the lines, which is called a directed graph, so that essentially A and B, basically like A could have B as a neighbor, but B could not have A as a neighbor. Make sense? Alright. So, as the game progresses, dedicated players can grind their way through quiz-like minigames in order to impress their peers. However, adding friends to one's friends list remains the cornerstone of the game. The bigger the friend list, the bigger the player. Okay. The object of the game is to have the biggest friend list, that is the most friends. Your task here is to take a list of friendships and determine the winner. There may be more than one person tied for first place. If so, your program should list them all. Okay, cool. So, the first line of input will contain the integer f. 1 is less than f is less than 1 million. Okay, that's fine. Each of the following f lines will be of the form AB, where A and B are different player IDs. This indicates that player A is friends with player B and vice versa. All player IDs are integers between 0 and 1000 inclusive. No friendship will ever be listed twice. That's fine. Output should contain the list of all player IDs that are tied for the biggest friend list. These IDs should be given in ascending order. Alright, fair enough. Okay, so how are we going to tackle this problem? So first of all, it's clear that we need some sort of structure to store our friend list. And obviously, since this whole workshop is kind of about graphs, we need a graph to store our friend list. Fair enough. So let's do that. So what we're going to do is we'll just start coding. And what we're going to do is we're going to make a graph. Okay, hopefully everyone can see my screen. This is good. All right, so what we're going to do is we need to make a graph that stores the friends. So in other words, we have a dictionary of lists, and each vertex or node is hashed to a list of neighbors. Okay, so how are we going to do that? So first let's read the input. Let me paste my sample input into the input file. So let me get up my input file. It's right here. And what I'm going to do is I'm going to paste my input in here. I hope that came up properly. Yes, it did. Okay, so now I'm going to leave that and go back to our program. So what it tells us is that we'll first get an integer f, where f is less than or equal to 1 million, which is the number of pairs we're going to get. Makes sense? So let's input f. So let's make an input file. Input file is open list in.txt. And what we'll do is we'll have f is map int. Oh, actually, we can just do this. Int input file dot readline dot input file dot readline, because we only have one integer to read. That's fine. Okay, let's print f. Actually, let's just read everything now. So for some variable in range f, we'll read our AB. AB is map int f. Oh, sorry, not f. Input file dot readline dot split. And let's just print AB. And we're going to also print f. So we're going to run this, and hopefully it shows up in my shell. I'll redirect to it. Yep, it does. Let me get the shell output up for you all to see. It's right here. Great. Okay, so let's get back to our program. We've now read all the input. So what we're going to do is, inside our program, we need to make a graph. So let's make a graph, and we'll call it graph, which is a very creative name, and it will be a dictionary. Okay? So what we will do is we will do something like this. Okay? So we need to add b to the list of values for A, and A to the list of values for B. Alright? So what we're going to do is we are going to do the following. So we will write graph. So we're going to just do it. We're going to play a trick. We're going to try and see if graph of A exists, which means that if we already have a list inside there, then we'll just append it, else we will create the list ourselves. So what we're going to do is we're going to try this. Graph A dot add B. Oh, in fact, we might even make that list a set instead of just an ordinary list, because it's a nice modification and it allows us to also do our membership checks in O1 time, in constant time. In this case, we don't need it, but it's a useful thing to have. All right. So graph A dot add B. We will accept a key error. And if it doesn't exist, then what we're going to do is we're going to write graph A equals set, and then do the same thing, graph A dot add B. And in a similar manner, we'll add graph B dot add A and accept the key errors. Graph B is a set, and graph B dot add A. So what I'm doing here is that I will try and add B to the list of neighbors for A, or the list of A's friends. If A does not have any friends, then just create a friend list for A and then add B to it. If it does, then just add it. So hopefully that should make sense. So now what we're going to do is we're going to print the graph. So when I do that, we should get a dictionary as output, which I'm hoping happens. Yep, we do. Let me open my shell so everyone can see it. Great, so we have a dictionary like this. 5 is hashed to 4 and 6, 6 is hashed to 5, 0 is hashed to 1 and 4, 1 is hashed to 0, 2 and 4, 4 is hashed to 0, 1 and 5, and 2 is hashed to 1. Okay, so we actually know who is friends with who. The next thing we need to do is actually answer the question, which means we need to determine who has the maximum number of friends, or firstly determine the maximum number of friends, and then determine who has that maximum number of friends, and then sort that. Okay, so that's what we'll do. So we now need to find the maximum number of friends that someone has. So what we can do is, just like a normal dictionary, well, graph is just a modified dictionary. It's a dictionary of sets or a dictionary of lists, right? So we can just iterate it over it just like we do with a normal dictionary. So how do we do that? We'll just write for person in graph num friends is the length of graph person. So what I'm doing is I'm taking some person in the graph. I'm finding how big their friend list is. So graph person is the set of all of their friends, and the length of graph person is basically how long that set is, which is how many friends they have. Make sense? So next, what we're going to do is we know this. So let's make a variable called max friends is 0, and if num friends is bigger than max friends equals num friends. Let's print out max friends. So we should get 3 here, because 1 and 4 have 3 friends. Let's see if we do. Yep, we do get 3. Let me get my shell output together. Yep, we get 3. Oh, sorry, I didn't put my Python on, so you guys couldn't see what I did. There we go. Yeah, for person in graph, num friends is the length of graph person, meaning that I want to find out how big that set is. How big is the set of a certain person's friends? And if it's bigger than however the maximum number of friends is, the maximum number of friends for a given person is, then we just update that maximum. Because we want to just find the maximum number of friends that any person has. So we keep a count of that. And if we find a person with a larger number of friends, we just update the maximum. Okay, now we know the maximum number of friends is 3, so let's find everyone with that maximum. Okay, so let's do that. So for person in graph, let's just make a list, all people with maximum friends. If graph, len graph person is equal to max friends, then all people with maximum friends dot append our person. So essentially what this means is that if we find someone who has the maximum number of friends, we're going to add them to the list of people we need to output. So this is the list of people with the maximum number of friends that we need to output. Yeah, I haven't commented anything on this try except stuff, but I hope I explained this in enough detail that you should be able to understand what this does. Of course, there are many other ways of doing this. You could have checked if graph A existed. You could have tried a bunch of different ways of doing this. There are multiple ways of doing this. This is just one simple way of doing it. Of course, there's probably something easier and shorter. I just did one simple way of doing it. Okay, so now we have all of the people with the maximum number of friends. What we need to do now is look at the specification for exactly what the output format they want is, and it turns out that they want it in sorted order. The ID should be given in ascending order. Okay, so let's do that. So what we have to do is we just do all people with maximum friends dot sort. So that will sort everything so it is in ascending order, and then we're good. So let's make our output file. Output file is open list out.txt, and we're going to write to that file. And what we're going to do is for p in all people with maximum friends, output file dot write string p plus a new line character. And then we're going to just close our input and output files. So input file dot close, output file dot close. And that should be the end of our program in theory. So let's just print all people with maximum, just to be sure. And we'll also check the output of the files too. So let's check our shell output. This is still loading. Okay, it gives us 1 and 4. Let's put our shell output in there, which is exactly 1 and 4. And then what we're going to do is we're going to check the result of our output file, which hopefully should be there. Okay, I think I need to close this and then open everything again. Let's do that. Let me open listout.txt again. And it has 1 and 4. Let me just redirect everything. Yeah, it has 1 and 4 in it. Great. So that is our output. So I think we are basically done with this. Of course, you can submit it and do all of that sort of thing. I highly encourage you to implement this yourself. But I think we will move on from here. This is pretty self-explanatory. I won't dwell on this too much. So we'll now look a little bit at graph traversal. And traversal is all about being able to go through the nodes of a graph and being able to look at every or search through a graph to find something. All right. So let me figure out how to get my video capture back. Where is my video capture? Up the top. There we go. Okay. Great. So let's talk a little bit about traversal. So traversal is simply the process of searching through a graph. So essentially, what does that mean, right? So we know that graphs are a powerful model of like a structure in general, and if you can formulate a problem dealing with graphs, you're probably pretty close to solving it, right? So what you want to do is you want to visit every node or vertex in a graph. Because we know that a lot of problems where we have to work on a data structure involve us visiting every node. Okay? So that's one thing we need to be able to do. All right? And we want to do it in a specific way. So essentially what we want to do is a specific type of traversal where we try and like search for something. So there are two big types of traversal, all right? How do you visit every node in a graph, and how do you do it properly so that you make sure you see everything? So here's an idea, okay? Let's say I have a bunch of nodes, A, B, C, D, and E. Okay, something like this, right? So one way of trying to visit every node in this graph is if you start at A, and then you visit all of the neighbors of A, like this, and then all the neighbors of the neighbors of A, and so forth. Okay, that's one way. So the whole point is you keep a list of nodes that you haven't visited, and you always visit a vertex that is one node away from a vertex that you have visited. So for example, we start at A, we can visit B, C, B, D, and E, because they're exactly one node away from something that we have visited. Now once we've visited B, D, and E, we can visit C, because it's one node away from something that we have visited, which is B. And it's not something that we visited already. Make sense? Okay. So how do we implement that sort of thing? Okay, here's how we're going to do it. So what we'll do is we essentially keep track of a frontier, which is a list of nodes, or right vertices, that are one node away from something we have visited. And in order to do that, we'll basically just keep these things in what's called a queue. We'll kind of go back to what a queue is a little bit later, but just imagine it as a list. imagine this as a list for now. Okay. We also need to keep track of things like what neighbors we visited, what nodes have we visited? And what data structure might be good for this? Well, what we need here is a set. So we need a set. Okay, because you can just check for a given node, is it visited, is it not? So for example, if x in visited, or if x in seen, then obviously this will return true and it will take a small amount of time. Okay, that's great. What other sorts of things do we need? We might also need something to keep track of where we came from. So it maps a node to its predecessor node. In the search order. Okay, so these are the sorts of data structures we'll need. And obviously we've seen that the data structures that we're actually going to use are things like sets, lists, and dictionaries, things that you're already very familiar with. So that's really good. Okay, so now what we're going to do is we're going to essentially implement a traversal of some part of a graph. Okay, so here's how we're going to do it. Okay, so let me create a new file. Let's just call this traversal. And let me make sure that it can actually be viewed. Okay, so I think everyone should be able to see this once I do that. Okay, we can now see the file. That's good. Alright, here is an idea for how to traverse a graph. First, let's make a graph. So let's do the one that we saw in the previous example that we wrote down. So let's have A is connected to B, D, and E. B, D, and E. B is not connected to anything. B is not connected to anything. Oh, B is connected to C, I'm sorry. B is connected to C and A. Cool. So A is connected to B, D, and E. B is connected to A and C, and everything else is connected to A. So, oh, sorry, C is connected to B. Yeah, C is connected to B. D and E are connected to A. So D is connected to A, and E is connected to A. Okay, let's just check that. So A is connected to B, D, and E. Yep, good. B is connected to only C and A. C is only connected to B. D and E are only connected to A. Okay, great. So now what we're going to do is we're going to implement essentially a traversal. So here's how we would do it. So define walk, G, and a source. Okay? So the source is where we start from. And G is just a graph. So takes in a graph G and a source node, so starting node slash vertex S. Oh, sorry, source in this case. So what we'll do is we'll first make a set called Q, and this will be a set of nodes to visit. So this is our frontier. Okay. What we'll also do is we're going to add the source. Actually, let's make it a list and append the source to the queue. Okay. Now what we're going to do is we're going to say while the queue exists, we're going to take a vertex out of the queue. So we're going to write u is q.pop. And what that does, what pop does, is removes the last element in the queue. So find an element to visit. And what while q does is it just says while there is an element to visit. Okay? Then we're going to remove an element, so we visited it. Next we'll write for each vertex v in G sub u. And what that means is that for each vertex in the neighbors of u, then we're going to write q dot add v, or dot append v in this case because it's a list. And now we can do something interesting, okay? Let's make another structure called P. And what this does is that P is a dictionary that maps nodes to their predecessors. So what this does is it allows you to know what the search order was. Okay, so what we're going to do is we'll modify this and we'll say if v not in P. The reason why we're doing this is that we don't want to visit vertices that we've already seen before. So if v was in P, right, if v was in P, a dictionary that maps nodes to their predecessors, it would have a predecessor, so we would have seen it before. Okay? Then we would append this to the queue, and we would set P sub v equals u. So that means that the predecessor of v is u. So if v was in P, we would have visited it before, but it's not. So we add it to the queue. It's something that we're going to visit, and we set its predecessor. Okay. So now what we're going to do is just take the keys out. So keys, and for each key, for k in P, and we're just going to return the keys. And what this does is it's basically just going to allow us to walk through a particular component of a graph. All right? So whenever we go through a graph, what this will do is we'll start at a certain node, and then we'll go through its neighbors and so forth. So let's try and run this. Maybe I've made a few bugs. We'll find out. Looks okay, but maybe there are a few bugs. So let's run this. So what we'll do is print walk graph, and we'll traverse it from A. Okay. So this will run. And what we'll get is essentially a list of nodes. So, hang on, BDEAC. Essentially, that's what we visited. Cool. Okay. So, yeah, this allows us to walk through a particular component. Now, what we want to do is make sure that we walk through in kind of a particular order. And we'll get to that probably next week. But the whole point is that we're basically just going to be able to walk through a particular component and make sure that we've seen all of the vertices and add them and keep track of the search order. Okay, this is really good. So what we're going to do soon is kind of look at well-known traversal strategies like breadth and depth first search. So I'll give you an overview of them because we don't have too much time. So I won't implement them here yet, but we will next week. So the general traversal works okay. It traverses each particular node in a particular component of a graph, like a particular connected part of a graph. Obviously, if there are parts that are disconnected, you have to search particular parts in order to find out what you haven't seen. That's actually pretty easy to do. What you simply do is you just look for a node that you haven't seen before in a particular component, and then just add that, and then keep running this walk function. All right. The only place where this falls short is that we have no real control over the order of the vertices that we visit. Okay. So here are some examples. Okay. Suppose we wanted to find the shortest path from some vertex to another vertex T, like in some sort of graph like this. In this case, we want to traverse all of the nodes that are one node away, followed by the ones that are two nodes away, and so forth. So this sort of traversal is called breadth first search, and it's very easy to implement with a pretty simple modification of our traversal function. Essentially what we want to do is we want to change our queue, which is just a list, into something called a double-ended queue, or a deck. In this manner, we don't want to just pop off any node. We want to pop off the first node or the leftmost node in the order. And this deck data structure, I'll actually write it in. It's called a deck data structure. Essentially allows us to do this to pop the leftmost item in a list in constant time. The reason why is it's a generalization of something called a linked list. A linked list is basically just a bunch of nodes with links. So for example, A is linked to B, is linked to C, is linked to D, like this. And maybe these nodes also have reversals and things. And the reason why you would want this sort of structure as opposed to just a contiguous slab of memory like an array is because if I wanted to insert a vertex, if I want to insert E somewhere in the middle of an array, I'd have to actually make space for E, and then, I'd have to make space for E in the middle of the array, shift some elements back, shift some elements forward, depending on how you implement this, and that would take O of n, or linear time. But if I had a linked list, what I could do is simply make a connection from B to E, and then make a connection from E to C, and everything would be okay. So it all depends on kind of the structure of the data that you're working with. But a deck is simply, or a double-ended queue, is basically just a glorified version of this linked list thing, which makes insertion and removals very easy. And there's a cost of that, which is essentially the access is hard. You won't be able to, say, access the ith element in your array like you would with in your linked list like this. Right? You'll only be able to do this, you'll only be able to do that with an array very fast. With a linked list, that would be extremely slow. So there's kind of a trade-off to using these particular sorts of structures. And that's the reason why you would use this particular specialized data structure for this. So I think we might We might stop there. Actually, I'll explain depth first search a little bit as well. So depth first search is the other way. Instead of visiting things that are one element away, one node away, two nodes away, and so forth, depth first search simply proceeds as far down as possible, then backtracks. So for example, if I had something like A, which was connected to, actually I'll get my camera out so I can show you this. So for a depth first search, if we had something like this, A, B, C, D, E, instead of going for A and then for B and D and then for C and E, it would go straight down this path to C until it saw the end, until it got to the end and couldn't go any further and it had to backtrack. It would backtrack all the way up to A and then try this branch, go all the way down to F. And whenever it can't backtrack without having seen everything, it'll stop. So there are kind of two types of ways you can do traversal, and one might be better or worse than the other depending on what sort of thing you're going to use it for. But we're going to cover all of that next week, a little more on how to implement breadth first search and depth first search and how to use these specific types of traversals for different sorts of purposes. All right, I think that's it from me. See you around in the next workshop next week. Bye.